Let me start. Yeah, and let me also share screen for you. Now you should be able to share screen, I believe.
All right. Can you
Yeah.
guys see my screen?
Yes, we do.
All right.
Let's maybe speak a little louder if possible. Oh,
Sure. Can you hear me now?
yes, yes, excellent. Let's proceed.
All right. So I hope you guys are doing well. Today I'll be talking about astrophysical turbulence, which I believe it's really fascinating. My name is Jose Javier Colon. I'm a PhD student in mechanical engineering, and let's start this. So, why it's so important turbulence in astrophysics? Well, actually, astrophysics uh, plays a fundamental role. Turbulence had a fundamental role in the creation of galaxies and planets, which is pretty important for us. And basically, the way that turbulence is responsible for the creation of planets is by transporting the energy and the mass from uh, massive clouds of dust and matter, and then it also transport the angular momentum of such bodies, also the chemical mixing between all the matter that is in those big clouds, and also an important role is the generation of magnetic fields and also the variation of them. Um, for example, in this picture, if you guys can see my uh, the picture and the arrow of my mouse, this is an accretion disk, and basically what is happening is that you have a black hole, which is the really bright uh, circle, and this black hole is consuming all the matter and the dust and the energy from around. And if you see right here, you have all these particles that are behaving as a fluid, and there's turbulence between them, and that cause them to collide and then create big, massive planets. And we are going to be explaining that uh, forward. And also, um, phenomena that happens in solar systems, like in the sun specifically. Um, it's very important, the turbulent flow, uh, and then in the magnetism of those planets. So the characteristics of turbulence in the astrophysics, this is are the most important ones, and basically what turbulence does and at astrophysical level is that we have uh, a big dissipation of energy by radiation, and this helps the matter that is colliding with each other to lose some energy, and then this will help to when those bodies collide to each other to stick together, which is the next point, which is self-gravity. And by that, that means is that when two objects collide, instead of bouncing back from each other, they stick together. And that's how the planets and stars form. Also, um, turbulence has a very important role in magnetic fields and how they are produced and how they have different vibrations. And also, it's very important the compressibility of these fluids that are involved at astrophysical levels. Um, so if we talk about planet births, uh, because the turbulence that happens at that level helps in the transport of mass when you have, like, for example, asteroids and big chunks of metals or different materials, and uh, those when you have forces that are making those uh, mass to collide with each other in a turbulence manner, they start creating big bodies. And also because of the self gravity, they stick together and they will start forming what we know as planets. And the sphere form, it's because of the angular momentums and all of that. And it's the basically the turbulence, it's making all of that. Also, you have energy transport and dissipation, and if you have high kinetic energies, when you have a collision, matter, uh, when they collide with each other, they bounce back because there's a lot of energy involved, and the gravity forces are lower than those forces created by the kinetic energy. So when the turbulence helps dissipating these energies, then uh, gravity forces are higher, resulting in the creation of bodies that stick together with each other. And we will see a picture that you can see better what I mean about that. And then the mixing, which enhance the collisions of the matter and also creates an altered magnetic fields. And what I mean by this is that you have fluids that are electrically conductive, and because of the turbulent flows, they are mixing together, and they behave in a form that creates dynamo effects, uh, very similar to the ones in electric motors. And by doing that, you create magnetic fields, which is very important for astronomical phases. So in this picture, if you can see the picture moving, I hope everyone can see, you have uh, a lot of particles that are behaving as a fluid, and they are really chaotic, and you have a lot of turbulence, and you see all this mass being transported and be colliding with each other, and the energy is being dissipated, so the gravity forces are higher, and it makes that every time that matter is collide with that big body, they stick together, and that's how uh, the planets and star are created. And also, you have to think about that because all of those particles are mixing, you're creating magnetic fields. And you have also the angular momentum that is happening. So that's why um, the planet is moving in that circular way. If we keep going, also in the sun, when we study the sun, there's a lot of turbulence involved. For example, this you can see in my cursor these solar flames. Uh, there's a lot of energy involved on them, and there's a lot of magnetism involved. And when these solar flames wants to separate from the sun and they come back to the sun, they release a lot of energy. It's like an explosion of energy. And this is mostly due to turbulent phenomena that is happening in there. And also because you have a plasma, this like behaving as a fluid, and you have turbulence inside that fluid, the magnetic fields are difficult to understand and difficult to predict. So the scientific community is trying to come up with new ideas, new equations to try to understand how these systems behaves and how the solar flames happens, or how the magnetism in Earth or in different planets behaves in the way they behave. Um, and you can see that one important thing is that the flows in the sun are really turbulent and they are disordered. There's a lot of disorder in all size scales. So you have big scales and you can see a lot of turbulence, a lot of chaotic movements. And then when you start going smaller in scales, you will see the same thing. And it's really difficult to predict. Um, so if we continue, uh, And then in order to understand this behavior, because turbulence in astrophysics is really very related to magnetic fields, we use something called magnetohydrodynamics. And basically, what magnetohydrodynamics means is that we study the dynamics of electrically conductive fluids, such as plasma, uh, liquid metals, salt water, all of that, and we see how they behave uh, with each other. And basically, uh, what we saw, it's kind of a small representation on what is happening at astrophysical levels, which is bigger scales. And these studies help us to understand the dynamo generation fields on planets, on the sun, the process of magnetic reconnection, which is the solar flare when it wants to separate from the sun, but then it come back to the sun and release a lot of energy. Um, it's also helped us to understand and being able to come up with models, mathematical models of clouds of particles that can help us understand and how the turbulence evolves through time in these big, massive stars, and also uh, the shapes and interactions of the structure of, for example, the sun, which is plasma mostly, and how that interacts with the turbulent flow. Um, and also, magnetohydrodynamics is used a lot in propulsion systems. Um, yeah, I think also for 3D modeling, what the scientific community does is they take Navier-Stokes equations and also Maxwell equations to be able to uh, come up with a realistic model of turbulence in astrophysical forms, because uh, compared to Earth, when you have turbulent flow here on Earth, it's not that related to magnetism, but when you go out, then you have other forces and other dynamics, and then it makes it more complicated. So they need to use those equations, and day by day they come up with new, more difficult ways to understand and how to model all of these systems. Um, so basically, this is the end of the presentation. This is the resources. I hope it was interesting topic. I know I went in a basic manner, but it's a lot that you can learn from this, and you can go really deep in how to understand everything. If you have any questions, I'll be happy to
Okay,
give answers.
thank you very much. Thank you, our presenter. Thank you, Jose. And you know, again, this is one more topic that I say every year somebody make a typical presentation on space, on astrophysics, astrophysical turbulence. This is really some hot topic, and basically really what people try to dive in astrophysics, especially since myself I deal with combustion, with turbulent combustion. It's very common practice that people try to deal with astrophysical combustion, with supernovas, accretion, forms of planets, forms of stars, how it make happen. It's really very interesting topic, and I may comment on this that my typical phrase, like when like physicists and engineers write text and read textbooks, astrophysicists write and read detective stories, because really we know very little about what happens in space, and it's really amazing that we can make conclusions based on this. We really know very little. We know about stars, that we can estimate what is a star. We know how it emits lights, so we know how intensive it is. And we may calculate how far is it, so we can calculate its mass. And based on these two parameters, we are able to describe all these features that we talk about. It's really something amazing. Anyway, thank you, and make please questions from the audience.
Um, uh,
Yeah, Latif, please. You should mute yourself. You are muted now. Unmute yourself if you talk something.
Okay, sorry. I didn't know. I'm really interested in astrophysics, and I've been kind of thinking about magnetohydrodynamics. So I have this question about how the magnetic effect is coupled into the hydrodynamic. Can you, I mean, Elite, can you throw more light on that? I mean, I'm trying to understand whether we have, I mean, what is the source of the magnetism? And then how does it interact with the masses around? Is it because the masses are, they're just, I mean, ferromagnetic material, or because they are charged, and since they are moving and they're charged, then some forces act on them? These are the things that I want to understand.
Well, so yeah, so basically to have these dynamic effects due to the magnetohydrodynamics, you have to have materials and matter that can conduct electricity.
Yes.
They're electrically conductive.
Okay.
Otherwise, you won't have this kind of magnetism effects on each other. Then you will have different effects like gravity or something like that to being able to interact with all those bodies. But
Okay,
basically, yeah,
I think it kind of makes sense now. Like,
yeah,
if you have the particles and they are charged and then they are moving, then they create magnetic field around them. If a charged particle is moving, it creates a magnetic field. And
exactly.
then because of its magnetic field, it can exert a force on another charged particle that is moving through its own field. So I think that's what I am looking for. Yeah. Thank you.
Yeah, sure. And also, you can see it in this way.
Mm.
You can have like metals that are moving uh, between each other, and they're
Okay.
interacting. If you have a magnetic field already in them,
Already,
you
yeah.
can create the move of particles inside
Yeah.
those metals. So this is
Okay.
basically the same thing. So the turbulent flow, it's
Okay.
like
Okay. Yeah. 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 Yeah.
yeah,
Okay. Okay. That's true. Thank you.
Okay,
sure, no problem.
thank you. More questions, please. And that's really good point that it is magnetic fields, magnetohydrodynamics, which is key point here. So sometimes people talk about competition between fluid effects and magnetic effects, and we talk about magnetohydrodynamics, right? So, yeah. So any more questions from the audience? I know Mohammed, I know you like this topic. Maybe. Do you have anything to say? No.
Not special.
Yeah, okay, I just asked because I know you're a fan of astrophysics and turbulence related to magnetical fields, especially second one. But okay, I just ask.
Yeah, one thing that I I like to add is the equations that we have to use in order to describe these systems should be self-consistent. That means when you have a charged particle moving, it produces fields, and these fields itself affect the other particles. So if this effect makes other particles to produce or exert new fields on your system. So everything should be self-consistent.
Right, right.
I think that is what I discussed. I
Yeah.
mean, the discussion I had with the presenter.
Yeah.
Yeah, about how the magnetism affects the most important thing you need is just the particle should be charged, and then if they are moving due to gravitational attraction, then because the particle is charged, that's going to create a magnetic field. Then the magnetic field is going to affect other charged particle that is moving, and then those particles field will also affect, I mean, the first particle. It's kind of a highly non-linear kind of differential equation system that you have that governs that the behavior.
Yeah. Mhm.
Yes, that's true. That's a good point. Yes, that's a good point about it. Okay, and also like what is crucial in astrophysics? It's it's typically very strong gravitational field. So if you talk about instabilities, it is a Rayleigh-Taylor instability which may dominate over other effects which may
Yeah.
turbulence. And everybody knows Rayleigh-Taylor instability. Well, idea is like why we call it Rayleigh-Taylor. Rayleigh instability, it's Rayleigh it says that if you have gravitational field, right, and if you have density gradient transfer to this field, it will be unstable. Like for instance, I don't know if you see my screen now. Yeah, I believe if you, yeah, you see me now, right, or not? What do you see on the screen?
No.
No. Okay.
Let me pass you the.
Yeah. Do you? Okay. What? I see myself now on big screen, but does anybody see it?
We cannot see
Yeah.
your screen, but we can see you.
Okay, yeah, that's okay, that's okay. That's what I want. Okay, so principle, if you talk about related instability, it's what? So imagine I have like typical, well, it's empty cup because I'm not very good in experiments, but typically idea is the following. Imagine you have this cup with water, for instance. And imagine I put some kind of cartoon here. And imagine then I turn it. So in fact, if there was water here and I release it, it may stay. Why may it stay? Because in my case it would not stay, but I just tell you example. Why would it stay? Because of a Rayleigh-Taylor instability. Because actually it's not unstable now because atmospheric pressure is enough to hold it. But when I remove such a plate, of course liquid will fall down. Why? Simply because of instability. Because any small disturbance of the discontinuity surface between liquid and between, let's say, light and heavy fluid, between liquid and air, will increase instability. If you have, for instance, water and glycerol on water, or some kind of, let's say, kerosene on water, they can stay like this because light is okay to stay on heavy body. But if you have mercury on water, it will not sustain because of this effect. Because you have density gradient and you have acceleration field. When you have gravity, when you have gravity, which works downstairs, and when you have density gradient, which is upstairs, delta rho, if they're in opposite direction, system is unstable. That is Rayleigh instability. And Taylor was who says that it's not necessarily gravity. Any acceleration field you have, it may be oscillations, it can be acoustics, it can be anything. As long as your oscillating field, as long as your acceleration is transfer, it's directed oppositely, in opposite direction to density gradient, you have this instability. And in astrophysics, that is a major force which creates disturbances, right? Okay. Okay. Okay, that was my comment. Any more questions to Jose, our speaker? No more? Okay. Then I stop. Let me just stop this recording. If no more questions. And so what? And let me.